Okay, let's start formally with what we did last time. We want to define cohomology of sheaves. So we start with a locally ringed space. XOX is a locally ringed space. And the first construction goes as follows. The claim is, and here we're working with a larger category, not quasi-coherent sheaves, is that if F is any sheaf of OX modules, the category of such sheaves is abelian, then F can be embedded into some sheaf I where this is injective. And I recall that injective means specifically as in any abelian category, so as an object in the category of OX mod. So these are not quasi-coherent. There is nothing. The only thing I ask is that over any open subset, F of U is a module over OX of U. So no conditions. And the sketch of the proof is very simple actually, but this is an important construction that everyone probably should understand. Is that well, step one, we know that if M is an A module, then M can be embedded into, well, let's call it, I don't know, J, where this is an injective A module, where A is a ring, commutative ring. And then we do something very funny. So step two, you take all points X in your topological space X. For instance, when you're dealing with a scheme, then you have plenty and plenty of stuff. You have generic points, etc. You take all points, and then to X, you have the following sheaf associated. You have the stalk, well, the stalk of the corresponding sheaf. You have local functions if you wish, and then you embed OX, X as a ring. So this is a ring into some I sub X, where this is injective now. And finally observe that you always have the following situation. If you consider J sub X to be the embedding of the point into your topological space, again, it's not necessarily a closed point, then what you can do, you can take the push forward J sub X star, sorry for the bad notation, of I sub X, and let's call it like nice I sub X. Then it turns out this is a good exercise. So step three, check that there is an embedding from F into the product of all those J sub X over all X in X. So you need to check two things, that this is injective. This is the first thing. And the second thing, the map is injective, and this is an injective sheaf. Okay, so this is a sort of general construction. And now you follow with the definition. The cohomology of the sheaf F on X is defined by first taking an injective resolution. So you construct a complex of the form F, you embed into an injective sheaf I0, you take the quotient, embed into, I1, and you continue this way. Second, you take the usual cohomology of the complex HI of the complex gamma, so global sections on X of I0 goes to gamma X I1 goes to etc. So in other words, this cohomology is the right derived functor of the global section functor of the global section functor. And just to remind you, what does it mean that it's a right derived functor? The main properties are the following. First, well, H0 on X or on any sheaf is just the global sections. Second, well, HI on X of anything is a functor. And third, there are certain connecting homomorphisms. I will just write that functorially, if you have a short exact sequence of sheaves FGH of modules, then to this, you have an associated long exact sequence, which starts with H0 XF, goes to H0 XG, goes to H0 XH. And then there is this first connecting homomorphism. Usually there is no index put in there. And you continue with H1 XF, H1 XG. Well, and it goes. All right. So of course, it is, as in commutative algebra, injective modules are very, very rare. I mean, not rare, sorry, they're very big. They exist, but they're very, very big. By the way, I commented last time, this is a construction from homological algebra, and of course, there are a lot of things to prove, for instance, that it does not depend on the choice of the injective resolution, etc., etc. But this is, if you wish, covered by some standard machinery from homological algebra. So there is a certain problem, and the certain problem is that it's very hard to compute anything using this technique. However, in homological algebra, so we already know, from homological algebra that one can compute these derived functors using what we call acyclic objects. Up. And what are acyclic objects? Well, these are the objects F, if sheaves such that HI on X of F equals 0 for I greater than 0. And by this I mean that if you start with a sheaf G and then you manage to find a resolution where all these guys are acyclic, then it turns out that you can compute HI on X of G by just again taking the cohomology of the complex gamma of X applied to F. So you just take the global sections on this resolution, and if you know that all the F are acyclic, meaning that they do not have higher cohomology, then fantastically you can compute the cohomology of your G. So there is a certain class of acyclic objects in the very general situation, and these are called flask sheaves. So by definition, F is flask, not necessarily a sheaf of objects, a sheaf of, sorry, of abelian groups of or anything, if for any open subsets V in U in X, the restriction from F of U to F of V is surjective. So it means that you can always lift a section from a smaller subset, open subset, to any larger open subset. So sections, there are plenty of sections. You can always lift them up. So here is a non-example. And it's a very important non-example. So the non-example specifically says that if you consider the constant sheaves, they're also called locally constant. So this is the sheafification of the constant pre-sheaf, say Z underbar on, well, on more or less anything, let's say on S1. So why is this on S1 with the usual topology? And this is not a flask sheaf, specifically because if I take my circle, and if I take for V, so this will be my, so the whole circle will be my U, and here's my V, which will be specifically disconnected. Then, of course, I can take the following section. I can take my section, then, well, what is my sheaf? Z underlined on V is, of course, Z direct sum Z, because I need to choose the value on one connected component and the value on the other connected component. But if the two values are different, I cannot lift it to a global section on the whole S1. And actually, this is a very, I should make a comment here, because in the usual topology, if you take as the ring of functions the locally constant sheaf given by Z, and if your space is nice enough, and if you compute sheaf cohomology, then you will get the usual Betti cohomology, or, well, singular cohomology, or whatever. However, this does not happen if your topology is very different. So an example now, though, if X is irreducible, an irreducible topological space, then any locally constant sheaf is flask. So here is another example. And this is probably, I don't know, this is a sort of proposition. So proposition, if I is an injective sheaf of OX modules, then I is actually flask. So what do we need to prove here? We need to prove that, again, sections lift, or in other words, for any pair of open subsets, the restriction map is surjective. And this is a good point to introduce a certain important operation, which is a little bit strange because it works only for sheaves of modules. It doesn't preserve quasi-coherence. This is actually a typical way to introduce non-quasi-coherent sheaves. So let some notation, let U be an open subset in X, and let F be a sheaf on X, then by F sub U denote the following sheaf. So F sub U on V will be F of V if V is contained in U, and it will be 0 if V is not contained in U. So for those that have seen it, you have the embedding of U into X, and then F sub U is nothing but the J shrink, if you wish, of F restricted to U. So now we want to prove that if I is injective, then it is actually Flask. Here is, I give it as an outline, as steps for you as a sort of exercise. So first, let V be in U, check that O sub V, well, that there is a short exact sequence. O sub V goes into O sub U, where here I look at it as an OX sub U. Now, second, since I is injective, hom, the functor hom into I as OX modules is exact. This is one of the definitions of being injective, which implies that we have a surjective map from hom from O sub U into I into hom from O sub V into I, and this goes to 0, O sub X. And finally, third, check that this is naturally isomorphic to I of U, and this is naturally isomorphic to I of V. In particular, you get a surjective map from I of U to I of V. This is some very powerful technique. I mean, the technique to remember is that actually for any sheaf, if you wish, sheaf of modules, hom from this J lower shriek of the structure sheaf is the same as this. I mean, this is some adjunction in a bigger generality, but we probably don't need it right this second. Okay. So our goal is to check that actually Flask sheaves are acyclic. Sorry. So here is a very good exercise for you. Let consider a short exact sequence of sheaves to be a short exact sequence. This is an easy exercise. The first exercise is if F prime is Flask, then we have, so in general, global sections are not exact, they're only left exact. But if the leftmost sheaf is Flask, then for any U, the sequence of sections is actually exact not only on the left, but on the right. So for any U, a subset in X. The second one says that if F prime and F are Flask, then F double prime is Flask. And we will use this just in a second. And the third one, if F is any morphism, is a continuous map, and F is Flask on X, then the push forward of F is Flask. So all of these are not very difficult. This is the end of the exercise. And as a corollary, we see that Flask sheaves have no cohomology. Higher. Okay. Well, how do we prove this statement? The proof is very funny again. It's quite formal. So consider. Sorry, embed. Let F be Flask. Embed it into an injective sheaf I. And consider the quotient. So what do we know about I? We know that I is also Flask. So it implies, because we checked that all injectives are Flask, so it implies by one of our exercises that G is Flask. All right. So now let's prove by induction that I has no cohomology, that F has no cohomology. Well, consider the long exact sequence of cohomology. What does the long exact sequence of cohomology give us? Well, first, we have the global sections, gamma on X of F, gamma X of I, gamma on X of G. Then goes H1 of X of F. And then goes 0, because this is nothing but H1 X of I, and I is injective. We can compute its cohomology using itself as a long exact sequence, well, as a resolution, and it's only a one-term resolution if you wish. But now this map is surjective. Why is it surjective? Well, it's surjective by one of our previous exercises. So we used both of our exercises so far. We used part 2 to check that G is Flask. Sorry, we didn't use this yet. We used the first part by saying that, for instance, the global sections are exact. So since this is surjective and the sequence must be exact, it implies that H1 is 0. But then, how do our short exact sequences, how does our long exact sequence look like? It looks like the continuation is Hi on X of I, which is 0, maps to Hi on X of G. Then there is a connecting homomorphism to Hi plus 1 on X of F. And then it goes to Hi plus 1 X of I, which is again 0. So this holds for all I greater than 0. But since we have 2 zeros on the sides, we have an isomorphism here. But now this guy equals 0 by induction. So this is an interesting way of doing induction. We kind of, for all Flask sheaves, we first check that H1 is 0. And then inductively, we see that for all of them, H2 is 0 because we have specifically this isomorphism. All right. So this is this is some good news. In particular, you can compute now cohomology using these sheaves. All right. Well, maybe maybe I should not comment much on this, but there is this theorem. As for general theorems, the theorem of Grothendieck. Which says that if X is an Noetherian topological space, of dimension n, well, of dimension d, then for any F sheaf of abelian groups, we have HI X of F equals 0 for I greater than D. Okay, so well, I will just maybe not prove it fully. So it's a sketch, a very, very big sketch. But this is a very interesting example of a typical proof by Grothendieck because it is something that we call, usually it's called divisage. It means that you need to reduce everything to very simple things or support it on something of much smaller dimension. So the first observation, which is worth remembering, first observation is that cohomology commutes with direct limits. So in particular, cohomology commutes with, say, even infinite direct sums. There is no problem. Second, by dimension reasons, second, reduce to the case when X is irreducible. So third, since this commutes with direct limits, you may assume that your sheaf is generated over an open subset inside X by a single section, meaning that there's a surjection from Z sub U into this thing. And finally, from this, use induction and the fact that Z is Flask. So yeah, this is quite a sequence of statements, but actually if you unwind them, or it's a good exercise to try to unwind them themselves if you don't feel well suited technically, then look it up in any source. You'll find that exactly these are the steps that are going on. So these are the general statements. All right, but we are, however, interested. So we're interested in first affine schemes and quasi-coherent sheaves. So just to set the notation, X will be spec of A, the spectrum of a ring. If you want your just coordinate algebra, if you want to think of varieties, so where A is a commutative ring, then remember that there is equivalence of category and equivalence between A mod and quasi-coherent sheaves on X. And if you have a quasi-coherent sheaf here, then to it, you simply associate the global sections. And otherwise, if you have a module here, then to this module, you will associate something which is usually denoted by M tilde. And by definition, this is such a sheaf that to a distinguished open subset given by a single function f, it associates the localization of M in F. And then you just use the usual procedure to sheafify. So in other words, we had a conversation about it last time. The whole big idea is that you don't get more sections than you need to. I mean, you need to be able to multiply by more functions. More functions on distinguished opens means that you can divide by this equation that doesn't vanish. And as a result, in the end, this is what you do. You just simply localize, or which is equivalent to taking yes, you can take it into you can tensor it just with the functions on the distinguished open. So here is a proposition that requires some algebra. I don't want to prove it immediately. Well, exactly, don't want to prove it, but you can check that if I is an injective module, as an A module, then I tilde is Flask. So this is very important because you need to remember that there is a certain distinction between being injective as a sheaf of rings and being injective as a module, say, for global sections. So far, we have, in a way, absolutely like no idea whether we have no idea whether these are the same things, but at least you can check immediately that this is Flask. And moreover, what is important, we've just produced from any injective module a Flask quasi-coherent sheaf. So as a corollary, we have a lot of things. So the corollary first is that on X, any quasi-coherent sheaf is acyclic. So this is probably a good analogy with the following thing that happens in topology. So in topology, you want when you compute cohomology, very often you want, or some other things, you want some neighborhoods, you use contractible neighborhoods. And if your neighborhood is contractible, this is specifically means that all higher cohomology of everything vanishes. So in this way, affine neighborhoods will look like contractible neighborhoods, if you wish. So no quasi-coherent sheaf has any higher cohomology in this way, and the proof is very simple. So the proof is let F now be the sheaf associated to the module M, then pick a resolution for M, I0, I1, etc. So in particular, the sequence I0 tiled, I1 tiled, etc. is a Flask resolution of M, which implies that it can be used to compute cohomology Hi on X of M, which now should be the ith cohomology of the complex global sections on X of I tiled. But this is the same as the ith cohomology of the complex I, because these are mutually inverse equivalences, global sections taking tiled and taking global sections, as we discussed before. There's this equivalence of categories. And this is particularly what we did. We applied tiled to this resolution, and then we got global sections back. But this is just a resolution of your M. So this is M if I equals 0, just the global sections as expected. And it's 0 if I is greater than 0. This is, well, a part of the definition of what a resolution is afterwards. All right. So in a way, on affine schemes, cohomology of quasi-coherent sheaves is absolutely not interesting. And I remind you that in algebraic geometry, we mostly are interested with quasi-coherent sheaves because we're interested in locally free sheaves, and which are vector bundles. And then, well, sometimes structure sheaves of points or things, but necessarily we all want to compute cohomology of vector bundles. This is the kind of ultimate goal. All right. Now, from this, actually, you can ask yourself, is it true that there are other spaces like this, which are probably not affine, which satisfy the following, the same property? And this is one theorem, very important theorem of Serre, that has a very short and nice proof. And this theorem by Serre, this is a criterion for being affine, which says that the following are equivalent. First, X is affine. Second, HI X F equals 0 for any F quasi-coherent and for all I greater than 0. And 3 is that H1, just the first cohomology on X of I equals 0 for any I sheaf of ideals. So again, sheaf of ideals, I always mean quasi-coherent. Well, now I just specifically said H1. Of course, people are, well, it's an interesting characterization between 1 and 2. I mean, 3 is as usual. Sometimes you can reduce to an even simpler statement. But the thing to remember is that that affine spaces are characterized by this fact that no quasi-coherent sheaves have higher cohomology. So here's the proof of this statement, which I find to be a very nice one. Yes, let me require, and this will be important, so that X is Noetherian. In particular, X is quasi-compact, but of course, I mean, for most of the times, we want to deal with varieties, and in such case, everything is Noetherian by construction. All right. So here is the proof. Well, 1 implies 2. We've just checked in the previous proposition. 2 implies 3 is trivial, because if all higher cohomology vanishes for all quasi-coherent sheaves, then in particular, first cohomology vanishes for all quasi-coherent sheaves of ideals. So it's we're left with 3 implies 1. And let me remind you that there is the following criterion for affineness. The criterion, it's very commonly used. It's a very good exercise if you have never seen it before. So assume you found functions f1, fn, global functions, such that, well, first, f1, fn generate the whole ring of global functions. And second, for each global functions, you can consider the corresponding open subset where this function does not vanish, and you want all of these to be affine. Then x equals spec OX of x is affine. So in particular, is affine. So once again, if you manage to cover, this is what it says more or less, if you manage to cover your, well, it's a little bit more. You manage to cover your space by globally distinguished opens. So distinguished open, you take a global function and you look at the set of points where it does not vanish. Assume that you found such functions and the corresponding distinguished opens are affine. If moreover you generate the whole algebra of global functions by the functions of your choice, then your space is affine itself. It's a very important criteria. So now let's use it. And let's use it using our cohomology thing. How do we proceed? We proceed as follows. So step 1, let x in x be a point. Then by definition of the scheme, x is contained in U, where this is an affine neighborhood. Denote Z, let Z be the complement to U. Then in particular, what we have is we have the ideal of functions. We have closed subschemes. One subscheme is Z union X, and the other subscheme, this subscheme, is contains the subscheme Z. So what we can do, we can look at the corresponding ideals. We have the ideal of functions vanishing at Z. We have the ideal of functions vanishing at Z union X. And what do we have in the quotient? Well, in the quotient, we have functions on specifically sorry, what do I want to say? Yes, we have the ideal functions vanishing on Z. Let's look at this quotient. G. So what in particular does it imply? Well, what are these functions here? Let's apply global sections. Apply gamma. We apply gamma, then we have the functions. Well, let me say it this way. We have global sections on X of I, Z union X. We have global sections on X of I, Z. We have global sections on X, G. And then what do we get here? Here we get 0, because this is H1 on X of the ideal sheaf of X. All right. So what do we conclude? We conclude that this map is surjective. All right. So since this map is surjective, in particular, I claim that we can find a function. What do I want to say? Double check with my notes. So this means that we can find, since this is surjective, and here we have a function which is not vanishing on the second. Wait a second. Yes, indeed. So let's recall that G. Now, what is G? G is just the functions. It's the skyscraper sheaf, if you want, of the structure sheaf. Well, of X. Sorry. It's a one-dimensional space. This is what I want to say. So these are the values. So this is the residue field of the point X, denoted by X and not P. So OX of X modular the big thing. All right. So what do we conclude? We conclude that there exists a function f, since in the global sections X of yod Z, such that f of X is not 0, because f of X is specifically the image under this map. So what do we conclude? We conclude that there exists a function f such that X sub f is what? It's d of f in the corresponding u which implies that it is affine. So again, what are our steps? Our steps are the following ones. We want to find an affine open neighborhood of a point X. We want to find it as an affine open neighborhood of the form X sub F, the set of points where F doesn't vanish. All right, what do? We pick any affine neighborhood. This is our first step. Then we consider the ideal of functions that are vanishing at the complement of this neighborhood. And now we look at all the functions. We want to find a function that vanishes at the complement of this neighborhood, but doesn't vanish at X. How do we do this? Well, we consider another closed subscheme. We take the union of Z and X, and then the quotient of the ideal sheaf of those functions vanishing at Z and those by those functions that are vanished both at Z and X is, of course, just the, well, it gives you the value, the fiber of the trivial bundle of the structure sheaf over the point X. So this is just the residue field at the point X. Now, since H1 of the ideal sheaf of Z union X vanishes, it means that the map here is surjective. But what is this map? It simply takes any function that vanishes on Z and takes it to its value here at the point X. Since the map is surjective, we can find a function such that it doesn't vanish at your point, and in particular, the corresponding principal open subset on your scheme will be affine because it coincides with the principal open subset in the affine scheme U. All right. So this is the hardest part is done. If X is an Noetherian, which implies that X is quasi-compact, which implies that we can cover X by finitely many such F1, Fn, all right? But now, what do we get in particular? We need to verify that this, so we're left with verifying that these generate the whole thing, generate the whole global sections of the space. So we need to show that F1, Fn generate OX of X. But what do we have so far? We know that we have a covering. If we have a covering, it means that we have the associated surjective map of sheaves from O sub X times N to X. So this is given just by multiplication by F1 Fn. And here we have in the kernel some sheaf F. But remark that there is a filtration of F on F. So if you consider it as a subsheaf in the middle sheaf, then of course F equals F intersected with OX sub n contains F intersected with OX sub n minus 1, etc. to F intersected with OX contains 0. But now each subquotient is an ideal sheaf. So check this. But now it means that f is an iterated extension of sheaves with vanishing h1, which implies that f has no h1 either. So this is just a simple application of the long exact sequence again. But if f has no h1, this implies that we have a short exact sequence. 0 goes to gamma of x of f, goes to ox of x to the n, goes to ox of x, goes to 0, because here we must have h1. So in particular, this map is surjective, which specifically means that f1, the ideal generated by f1 fn, is the whole algebra of global functions. And we have finally finished. All right. Pause here. So of course this is not okay, so this is not very plausible to use for computations. Maybe Daniel, can we have a 5-minute break, please?
Yeah, of course.
Okay, so let's have, because this is a decent place to stop, so you can probably pause the recording. All right, we're back with check cohomology, and this is one big thing in the which is very important computationally. So let me say a few words how it's done in general. So you start with X, any space, and say U, I will denote it by U dot. This is an open covering over some index set A. And here is where some interesting things begin, because there are many flavors of check complexes. So you put F to be a sheaf of abelian groups. So here's the first complex, check complex that we construct. First complex. And I alluded to it last time. So Ci will be the set of U F, will be the product over all alpha 0, etc. alpha I of F of U alpha naught intersected with U alpha 1, intersected with etc., intersected with U alpha I. And the differential of an element, let me denote it by S of alpha naught alpha. So the differential of S evaluated at I plus 2 terms will be the alternating sum of -1 to the power j of the restriction map of S of alpha naught alpha j removed alpha I plus 1. So the restriction, this will be always from some intersection alpha naught alpha j, this removed, u alpha I plus 1 to, well, the big one. And you need to check various things. You need to check that it's a complex. This is the first thing to check. The second thing is quite interesting. So assume, yes, check that it's a complex and put H check this cohomology with respect to the covering U of F to be the cohomology of the corresponding complex. All right. Assume V is another covering. And assume that one is given. So let V be indexed by beta, where beta is in the set B. Assume we're given a function, let's call it T, from B to A, such that V beta is contained in U T beta. So in such case, we say that we have a refinement of one covering by another covering. Construct, in such case, a morphism of complexes. And a question for you, in which direction? So this morphism of complexes will actually be different depending on the choice of this T. Third, which is quite a surprising thing, is that check that the map on cohomology does not depend on T. And finally, the fourth is you can consider the directed system of all coverings and all possible refinement maps. And in such case, what you want now is you want to put H check on X of F to be the limit of all H check over all possible coverings of F. So this works in a very general, in a very big generality, but of course the most important thing is for us is that in most cases that are interesting, this check cohomology, first of all, will coincide with the usual one, with the one that we defined, and second of all, we can restrict to very simple coverings. So our goal is to show the following. Our goal is to show that if X is Noetherian separated, and any variety is such, so the only thing that you are asking for is you are asking for the intersection of two affine open subsets to be affine again, and this is what separated implies. Then actually for any affine covering phi alpha H check of U of F, where F is quasi-coherent, is the same as H of X of F for F quasi-coherent. All right. Let me briefly sketch how it's done. So this is a sketch. And the first observation is you can order your set of indices and only consider the product over all F of U I naught intersected with U I n, where I naught less than I1 less than etc. less than IN. The general situation, you can, yes, you need to pick a total ordering, but this is more or less how it's done. All right. So the second thing that is important for us is that if you have, if F is Flask, then actually check cohomology vanishes for all open coverings. Equals 0 for any I strictly greater than 0. All right, well, how is this done? Well, it turns out that one can construct a Flask resolution of F such that its global sections is the check complex. And indeed, the resolution looks very simple. Namely, so what is the check complex? The check complex, as I've told you, you can consider these sections over first open subsets of your covering, then double intersections of your covering, then triple intersections of your covering, etc. So let's consider the complex instead. And the complex will be the following. Put C curly I to be the product over all I1, well, maybe not IN, sorry. I naught IN, and here you have the push forward, the inclusion if you wish. So this is again the complex, the push forward of F restricted to UI naught intersected with UIN. So we restrict our sheaf first to the corresponding open subset, and then we take the push forward under this restriction. But now check that this is a resolution. So now these are sheaves. This gives a resolution. these are now sheaves. And remark that these are flask if F was flask. So this is a very simple exercise, and this is exactly where we already, I told you we needed to prove that if we have a continuous map of topological spaces and you have a flask sheaf, then the push forward of a flask sheaf is again flask. All right, so we managed to construct a resolution by flask sheaves, but then the global sections of this resolution is precisely the check complex. So what do we conclude? We conclude that the cohomology of this complex on one hand, so on one hand it computes the usual cohomology, but on the other hand it computes the check cohomology. So in particular, we conclude that the cohomology vanishes. And finally, step three goes as follows. If so any quasi-coherent sheaf can be embedded into a flask quasi-coherent sheaf, and hint reduce to the affine case. Well, we'll use the affine case. And now the last point is, well, use induction. Consider F, G, H, where this is flask, and use induction. As we used before, maybe I don't want, so we don't have much time, don't want to discuss many questions here, but as a result, the most important thing that you want to remember is that finally cohomology can be computed using check resolutions, check cohomology, and an affine covering. So here's an immediate exercise that I suggest you do. Exercise. Consider a curve. What am I doing? Consider a curve given by a homogeneous polynomial in 3 variables. Inside P2, and assume that the degree of f is d. Assume further that the point 1, 0, 0 does not belong to x. So in other words, f does not vanish at this point. Then use the standard covering. Use the 2 opens, U1 and U2, to compute cohomology of x, and show that the dimension H naught of OX, so this is the dimension of H naught X over OX, is 1, and H1 of OX is 1/2 for d minus 1 times d minus 2. So this can be used, this can be done very much explicitly. Let me give some other standard examples. Yes, I forgot to say that another exercise, and this is directly coming from Flask resolutions, is that if f from x to y is a closed embedding, then for any f quasi-coherent or not, hi, well, let's say quasi-coherent, h1 of x of f is naturally isomorphic to hi on y of f lower star of f. As a corollary, cohomology on projective varieties can be always reduced, since by definition, if you wish, projective is something that can be embedded in a projective space. This can be reduced to computations on Pn. And this is where we come to another theorem of Serre, and the theorem of Serre specifically says the following. So let Pn be the projectivization of V, which is the same as proj of the symmetric algebra of V star. Then there is an isomorphism of, if you look at the direct sum of gamma over Pn over all O of t, where O of 1 is the usual O of minus 1 is the tautological bundle, O of 1 is the very ample bundle of t, then this is isomorphic to the symmetric algebra of V star. So this is the first part of t greater or equal than 0. Also, all of t for, and let me be careful here, for 0 greater than t greater than minus n minus 1 are acyclic. And finally, also, there is a perfect pairing given from H naught P n O of t times H n P n O of minus n minus 1 minus t going to H and P and O minus n minus 1. And this is isomorphic to K. And moreover, so these, this is the only cohomology. For of minus P, where P is less than or equal minus n minus 1. So you have only higher cohomology on these varieties. So this is the big theorem of Serre. This is done purely by computing cohomology on the using the standard covering of the projective space. I mean, there's nothing else happening. Just the cohomology of the projective space. So it has a lot of corollaries, this theorem. So corollary. Yes, one corollary is that if F is quasi-coherent on a projective space, sorry, if F is a coherent sheaf, not quasi-coherent. So let's switch to our varieties. If F is a coherent sheaf on a projective variety, well, say over a field, then all cohomology groups are finite dimensional vector spaces. And this is absolutely not true for affine varieties, because on affine varieties, you don't have higher cohomology, but the structure sheaf already is not finite dimensional. It's finite dimensional over the base field only if you have a fat point or a finite collection of points. And this is done by reducing to computations on the projective space. And second, if O of 1 is very ample, then hi on x f of n vanishes for all I if n is big enough. This will be also a very important point for us. Let us do the following, since definitely won't be able to complete in time. Let me formulate finally the final most important thing, and then next time we'll start with applications, because also I'm feeling a bit hot right here, and maybe I'm not fully recovered. So here's the final thing that I want to tell you now. So now let X be a smooth projective variety. And then if it's a smooth projective variety, then in particular we have omega, which is the cotangent bundle, which is a locally free sheaf. And if X is of dimension D, then we have the determinant, the dth wedge power of omega X. So this is called the canonical bundle, and it's actually a line bundle. In its simplest form, Serre duality which is a fascinating and incredibly strong statement, says the following. Let F be a coherent, a locally free sheaf then we can compare cohomology of F, which is the vector bundle, if you wish, given by F, and the dual vector bundle. So if F is a locally free sheaf, then there is a perfect pairing well, let's say isomorphism between hi on X of F. So this will be again over a field K. Say algebraic, say over C. Then there's an isomorphism between hi and h d minus I on X of F dual. This is the dual times omega X. And this is what it's called in its simplest form, Serre duality. All right, so we have basically all the players in the game and the big statements. So what we will do next time, I will spend a little bit of time giving examples and specifically how it all works for curves and very explicit computations, and a little bit for surfaces maybe as well. And then we'll talk about some more complicated tools such as higher direct images and and spectral sequences and how they help us compute various kinds of cohomology. So I think for today we'll end here, if you don't mind.